So for those of you in AP Physics 1, or if you took AP Physics 1 before, when we did work, we did the force parallel to the displacement. That's how we did the work calculation. But if the force isn't constant, the more general form is using work is the integral of force times the displacement, okay? So just like the previous lesson, we talked about work as being, you got to take the component of force parallel. Just remember, you got to have a force component parallel to the displacement. When you're doing this dot product here is indicating that those vectors need to point in the same direction. So we need to take the component of that force in that direction. But instead of delta x, you're going to make it dx. It's like you're breaking it into little chunks. And this is only useful if the force is varying or if the direction of the motion is changing, right? So it's not moving in a straight line. Then you would need to chop it up into little pieces and then can perform this. But in general, like, you're just going to execute an integral to compute it, right? And we just got to make sure we're doing the same direction here. So we have a time varying force is given by this over displacement 2 meters. How much work is applied to the box? You're just going to integrate f dx, and you're going to do the bounds over displacement from 0 to 2 meters. I should have been more clear here. It should have been from x equals 0 to x equals 2 meters. So you would just integrate this 2x squared dx, and then that would be 2x cubed over 3 from 0 to 2, and that's going to be what, 16 over 3 joules of work there, right? Let's do something a little more complicated with the vector notation. So you have a time-varying force here. Not a time-varying force. I don't know why it says time-varying. A varying force. The force varies as a function of position here. The box travels in a straight line from the coordinates 2, 3 here. So here's 2, 3, all the way to the coordinates 2, 5 up here in a straight line. So this is the path it's going to take. How much work is done by f of x? Now, you have to think of the force vector. The force here has a vector, has an x and a y component, right? It has an x component. You can think of it, the x component is 2x, and then it has a negative 3 over x as the y component, right? So when we're integrating it, we only care about the component that is parallel to the displacement. So like this guy right here. So when you do this integral, you're going to integrate f dx, but you want, when you're doing this dot product, you're doing the component parallel. So we want only the vertical component, the negative 3 over x dx. And what are you integrating from? Now we call it x, not really x technically. You're technically doing it, sorry, it's actually dy, right? And you're going from the y coordinate from 3 to 5. Now you might think like, what about this x in here? Do I change that x to a y? What does that x mean? You gotta remember what that x means. That x represents the x location. It's like the x coordinate of it as it's moving, like at different x coordinates. So in this case, during the entire motion, the x is equal to 2. So we would plug in x equal to 2 here. So don't just be like, oh, well, let me just replace it with y. You don't want to just be, you have to understand what that x represents. That x represents the x location of the force, right? And or of where the particle is acting. And so in this case, you're integrating from 3 to 5. The x is a constant that entire time. That's negative 3 halves dy. Then would be negative 3 halves times y would be the antiderivative from 3 to 5. And you get negative 3 halves, 5 minus 3. That's going to be negative 3 joules. And it does make sense that it's negative because the displacement is opposite the direction of the force. The force component was negative. It was pointing downward, right? Opposite direction. So it makes sense that we have a negative amount of work there. So be very careful. Don't think about just because I have a variable in there, I'm going to automatically just plug it in and integrate it, right? You got to think about what that variable represents and how it applies during that motion. What does that x mean in the context of that force there, okay?